Welcome. Today we're going to be covering the Guide to Computer Forensics Investigations. This is the 6th edition. The material all comes from Cengage. They own and control all copyright material. I'm just providing video lectures on the individual chapters for my courses using this textbook. My name is Arthur Salmon, and I'm going to be working with you throughout this book. Thank you. Chapter 3, Data Acquisition. In this chapter, we're looking at 4 main points. We're looking at evidence storage formats. We're explaining ways to determine the best acquisition method based off of certain scenarios, describe contingency plans for data acquisition, and explain how to use acquisition tools. Again, the focus of this chapter is specifically geared towards acquisition. So those are our 4 main areas. However, there's also things like validating, looking at RAID for acquisition, explaining remote network acquisitions. Those are all more advanced topics, but still have to be covered, and lists of other forensics tools available for data acquisition. Again, the main concept is data acquisition. How do we do it? How do we validate it? So the first big thing is understanding our formats. So we have things like our raw formats, and with that, our raw format is going to be probably the more common type. We have proprietary things like InCase, for example, uses a proprietary formats, and that's not really easy to be able to implement in other tools. So proprietary formats aren't always the best. We also have the Advanced Forensics Format, AFF, and again, that's not as widely used. The raw format is probably going to be the most common. So raw format makes it possible to write bitstream data to files. A bitstream is again a bit-by-bit copy. It's fast data transfer. Big thing is it ignores minor data read errors on the source. There's an issue with that. Data read errors on the source means hash values of the source may not be equal. So if we're looking at the source, the original evidence, and a cloned copy, the hash values may be different, thus no longer eligible for data collection. So that might be a concern. So we do want to look into the raw format and specifically looking at the hash values if there are minor read errors. Nice thing is the raw format, pretty much everything can reads. The disadvantage is storage. If you're capturing a 100 gig file, you need storage larger than 100 gigs because there's overhead to a large raw capture. As well as tools might not collect the bad portions of the drive or the sectors. Again, that goes back to the validity of the source evidence versus the cloned copy. The original versus the cloned copy we'll be working off of. Proprietary formats, again, each big manufacturer typically have their own. InCase is really known for this, and they have their own proprietary copy. The issue is, because it's proprietary, more and more forensics organizations have moved away from InCase because it is proprietary. InCase is expensive. So there are issues with that. Compression could be a concern based off of the formats. Splitting the files into smaller segments, again, that may or may not be a feature that's offered. Disadvantage, it's proprietary, meaning if you open it up in one manufacturer or one publisher's tool sets, you're going to be using that tool set, period. There could be size limitations, there could be other things. The big thing is, with proprietary formats, we have what's known as the expert witness compression format, and this is an unofficial standard, even though this is one that should be used. Advanced forensics format, it was developed by Simons and Garfunkel as an open source acquisition format. Love open source acquisition formats, so that is a huge plus. The design goal was to do good compression, no size restrictions, space issue, to alleviate some of the space concerns, space images, and looking for ways to pull metadata out of it a little bit easier. Simple design, again, multi-source, open source, multi-platform, not tying it down to specific tool sets, internal consistency check for self-authentication, all big things. Using the AMF for our metadata and an AFD for segmented image files. Again, the AFF is open source, so that is kind of one of the better options. Realistically, most organizations are still going to be using a raw format, but there are other options available. So now that we talked about things like size and formatting, so when we go to actually do the acquisition, what are we looking at doing? And that's a big thing. So when we're looking at acquisition, there's two types: live acquisition, static acquisition. Live acquisition is the unit is on, it's still processing, it's still doing things. So we can capture everything that's happening on the device we're trying to capture. So let's assume we're trying to capture a hard drive, for example. So with live acquisition, files are being written to and copied to and moving and just the typical interactions between the OS and the drive. Well, we can capture that. Or if the unit is off, we can capture that, and that would be a static acquisition. The unit's powered off and there is no activity on the drive, and then we would go ahead and capture it. So there is the in action or live acquisition or a static acquisition. So once we've determined the type of acquisition, then we could figure out what are we trying, or how are we trying to do that collection, or how are we trying to do that acquisition. So we can take the disk, we can take our hard drive. Could be an SSD, could be an M.2, could be any type of long-term storage. Are we going to put that to a image? So it could be an image file. Or we could put that to another disk. We could clone hard drive to hard drive. And that could be a straight one-to-one physical disk to physical disk. The entire physical disk to an image file. So that's these two. Or we could do a logical disk to disk or a logical disk to image. And that's looking at the logical disk, the volume portion, not the unused space. Then we have a sparse data copy of a file or folder. So maybe we're looking at just copying a directory or an object or a file instead. So there are pros and cons for each one of these. It kind of depends on what you're being allowed to do. Maybe you have a subpoena from a judge, and the judge says you're only allowed to review this folder on this computer. And that would then limit your analysis based off of that to that object. So that's when you'd be looking at this guy here. If it's unknown and it's part of evidence and there isn't a subpoena, there is another body granting you access to the device, maybe you're doing a full capture, or you're only capturing volumes of the disk or a single partition of a disk. Again, there should be some type of scope document outlining what you're going to be collecting. And again, the big thing is the method is all based off of circumstance. If you are in a corporate environment and HR or the company owns the assets, and HR is the granting or the governing body that grants you the access, and they say capture the volume. If that's your scope, then that's your work. If they say capture the entire disk, then you capture the entire disk. If you're working for law enforcement, again, there's going to be a granting body that tells you what you're allowed to collect and analyze based off of the circumstances of that situation. So let's look at creating a disk to image. And this is probably one of the most common methods because it's flexible and you don't have to worry about a drive failing. Not just that, you don't have to keep a bunch of sanitized storage media around. And the nice thing is, you can make more than one copy, assuming you verify the original and the clone. And you do that through hashes. You'd hash the original and hash the clone, and you would compare the hashes. As long as they are identical, you're good to go. And that means you'd be doing a bit-for-bit copy of the original drive. And what you could do is, once you have your hash value, you could do a clone, another clone, another clone, and you would do hashes for each one of these. And you would compare the hash to the original data. And as long as the hashes are all equal, then you're good to go. If one of the clones is not, then we merely discard it. The hash verified it wasn't a bit-for-bit copy. So then it's not identical to the original evidence drive, so it's not worth reviewing. Only the clones, a bit-for-bit clone of the original evidence, is going to be used for review, unless your scope of work is looking at a specific object or a specific volume, and then you'd be hashing those portions instead. A disk-to-disk copying is normally done when you can't do an image for whatever reason. And there are tools that can adjust the geometry configuration of a storage device, because the geometry configuration dictates the storage space. Though, keep in mind, we cannot go from like a 200 gig drive to a 2 terabyte drive by manipulating the geometry. That's not how it works. You can go smaller, you can't go bigger. And tools that are out there that do this are Encase and Xways. And again, Encase is kind of more going out because it's the proprietary of their software. And it's not that it's bad, it's just because of the proprietary portion of their software, you're seeing Encase less and less. So now let's talk about the logical acquisition or the sparse acquisition. And again, this is going to be a huge time concern, because when we do logical acquisition, also sometimes partition or volume partitions, this is basically when you have limited time, this may not be a good option. The logical acquisition captures only specific files of interest or based off a scope. The sparse acquisition collects fragments of unallocated, also known as deleted data space. So the logical acquisition is specifically going to capture whole files, things that are inside the scope of it, but sparse acquisition are going to be the fragments. Really good for large data disks. Also really good for email, PSTs or OST mail files that can be gigs large. And we can also be looking at RAID in this arena as well. Not so much the logical acquisition. I mean, you could, because you can capture data off of sections of the entire array if the RAID server is complete. If not, then would be doing sparse acquisition, but that's a whole nother level of complexity. So now that we understand the data acquisition process, we know we could be capturing it multiple different ways. When we are imaging it or we're capturing the image. Some considerations: size. How much space do I have to work with? If I'm capturing a 2 terabyte drive and I only have 2 terabytes free, is that going to be enough? Is there any type of compression that is involved? If we're using lossless, it might be more useful because we can compress some of the data files or the structure to a smaller image. Again, hash for verification. Always want to verify. And that means you could be using signatures for verification or hashing. Whatever the process is, you want to make sure that it's all heavily documented. You also must work with drives that are large enough when we are working with an image, unless we're using some type of lossless compression. If you are using a lossless compression, you might be able to use a smaller drive, but again, you do want to make sure that you have the appropriate storage for what you're working with. You also want to have the appropriate time for the acquisition. If you're doing a large acquisition, I once did a 20 terabyte RAID acquisition, and it took days. I set it, and I just watched the acquisition crawl through for my image. Luckily for that case, I had the time. However, you do have to keep that in mind. Sometimes time is not on your side. You also need to understand, where is the evidence located? If you're granted the authority to do a full bit-for-bit copy, you might be able to find evidence in the slack space or the sparse space, the deleted space. Not saying that you will, but you might be able to. But if time doesn't allow and your scope doesn't allow, maybe you're doing a volume instead of a entire disk. So what happens when something occurs? Is there a contingency plan for image acquisitions? First of all, we have our source, we have our clone, our copy, and you always want to make sure we hash both. You want to get a hash of the original source data and a hash of the clone. That way, we can say it's a duplicate copy, and as we clone out the image file, we can just rehash the clone, and all copies coming from the clone, if they are the same hash, we know they are the exact same copy of data. Always make sure we have 2 images of the digital evidence. That way, if something happens to one, we have a backup. And again, we verify via hashes that both copies are identical. We may take one of the clones and have it in a protected area on the host. We may have a read-only access to a clone. You could be using hardware acquisition tools or a write blocker, something to protect the data from being modified. In the age that we live in, be prepared to deal with encrypted drives. So if we're doing a live acquisition, we may be able to capture the memory and extract a BitLocker or an encryption key from memory. Whole disk encryption, like BitLocker, exists, and it has for a lot of time now, or some time now. So, understanding how to work with encryption is going to be more and more important because it's becoming more and more common. You may have to work with the user to get a decryption key, or memory or other path for that ability to decrypt the whole disk. Alright, so now that we have a basic understanding of how acquisitions and kind of how they can be stored, let's look at tools. So one of the big parts is there are Windows tools, there are Linux tools, there's Mac tools. It really all depends on your environment. So Windows tools might be things like FTK Imager. That's a pretty common acquisition tool. FTK Imager. And what that does is it allows us to do data acquisition. Again, acquiring evidence from a original evidence file way more convenient. There are some disadvantages. You have to have a write blocker, whether it's a software or a hardware write blocker. That prevents data from being modified on the source. Tools can't acquire data from disks from protected areas. And again, there are ways to get away from that if we're doing bit by bit copies. But again, that is based off of the acquisition tool. And one of the big ones is countries haven't always accepted the use of write blocker devices for data acquisition. So write blockers are not used in all countries. So that is definitely a consideration. So when I said write blocker, I said software or hardware. A hardware write blocker is going to be a physical device that sits between the interface for the hard drive and the actual hard drive itself or storage media itself. And it completely prevents the modification of data on that drive. It only allows for passive reconnaissance. It only allows for passive reading. No hardware changes, no changes whatsoever will be allowed to be written to the hard drive. For the software, we can have things like a Mini-WinFE or a Windows forensics tool, and that will basically mount the drive read-only. And from there, you can then capture the image. So basically, before booting, you connect the target drive as well as a USB drive. That USB drive is going to be your Mini-WinFE toolsets. After the toolset is loaded, it will list all the connected drives and alter your target device to read read-only devices, and then you can then start the acquisition. So there are tools out there for helping within the acquisition process. You have to realize, especially in our acquisition portion, that the source evidence cannot be modified. And so you have to get that there are Windows tools out there that may prevent it, both hardware and software. If we're doing it within the operating system, it's going to be software based. But verifying is important. So with Windows, we have things like the Mini-WinFE. In Linux, we have other tools that do the exact same thing using a Linux live CD. And essentially, the forensics live CDs don't access the media automatically. Thus, you don't have to worry about a write blocker. You can open up media in a live disk that will mount it as read-only, so you don't have to worry about any of the data being modified. Windows OSs and newer Linux automatically will mount and access the drive. The access of the drive modifies the drive. People don't think about it, but even just turning on your computer generates logs. And that right there is modification of the evidence. So we have to be careful. Also keep in mind, Linux can access the drive that isn't mounted. So there are some options there. Mounting is not always necessary because Linux keeps everything as a file. You can have things like Kane or Kali or the SIFT workstation done through SANS. Kane is probably one of the bigger ones. We have a Sleuth kit that also does the exact same thing. So there's a lot of forensics live disks out there configured not to mount, or if they are going to mount, they're mounted only as read-only. And these tools have been out there because, again, open source, as well as this discipline has been growing. So preparing the target drive for acquisition in Linux, keep in mind, if we are capturing a Windows environment like Windows FAT or NTFS tables, Linux can create the partition tables. We may have to use commands like fdisk to list, create, and delete partitions. We also may have to use the mkfs ms-dos command to format the FAT systems for Linux, because again, FAT and NTFS were made to work within Windows. Linux can read the formats, but there are some prep that needs to be done beforehand. So if you have a functional Linux computer, we can follow the appropriate steps in the reading to prep a target drive for acquisition. And we're also going to do this as a lab in separate videos. For acquiring data, normally we'll use a dd command or data dump command, and that's also a file format that was not discussed earlier in the chapter. This can both read and write from media and data files. It does create a raw file format that almost any computer can use. So when we're talking about a raw format in Linux, we're normally talking a dd file, and again, that's a raw format. There are some shortcomings of the dd command. It does require more advanced skills than the average user. It does require some Linux skills. It doesn't compress data, and the dd command combined with the split command will segment the output into separate volumes if that is something that you want to do. Acquiring data with the dd command, there are steps in the book that outline how to make an image of an MTFS and a FAT disk. And there's also the dcfldd command in Linux for acquiring data. If you don't want to use a acquisition tool already built in, Kane, Sift, Kali all have acquisition tools built in for acquiring data. So if we are using the dcfldd command, we can specify hex patterns, log errors. There's a lot of hashing options, and we can also look at the status of the progress of the acquisition, because that's one thing that not all the tools do have is progress bars. And I've encountered that where I've started a acquisition, had no progress bar, and had no way to estimate time to completion, so we just kind of sat, waited, and waited, and waited, and eventually it finished. The dcfldd command also split the data acquisition into segments, if that is something that you want it to do, and there is a way to verify the acquired data using hash options. So we already talked about Windows-based tools. One of them is being the Forensics Toolkit, or FTK, AccessData. AccessData is the group that publishes the toolset. FTK is the Forensics Toolkit, and Imager, or Imager Lite, is the tool that we'll be using to take source evidence and create a evidence to image file. This makes disk to image copies of our evidence at the logical partition, physical drive level, or segment data, or more. And you can also do this as a live CD as well. Normally the AccessData FTK Imager is used for static acquisition. You can use it for live acquisition, but that adds in some layers of complexity. Here's FTK Imager version 3.118, and again, it's broken into several panes. The big thing is capturing the image. And FTK Imager can't acquire a drive host protection area. We already know that. We have to use a write blocker, whether we are using a software or hardware. Basically, boot into Windows, connect the evidence using a write blocker, target the write blocker so that it's functional, start FTK Imager, create a disk image using a physical drive option, and then you can see your locations from there. So here we have a physical drive, a USB drive that we're capturing. That's our source, and it will even say source. And we can then put it to a different location. If we're capturing From a disk to disk, we could say source and destination. If we are capturing source to image, then would select the image type. Again, RAW or DD. That's going to be the big one. AFF is also there. We have an in-case proprietary one. We don't want to use that. DD or AFF are probably going to be the most common one. DD probably the first option. Then when we are done, we click Next. We give it a case number, an evidence case number for working with multiple pieces of evidence or multiple artifacts, a unique description, who's doing the work, and if there's any notes. That way, as we're generating a report for our acquisition, we can have all of this already in there. Then we want to give it the destination, and we want to name the image file. And again, we can use a file formats. We can use a way to fragment if we want to fragment, or we can do a 0, no fragmentation. We can also do levels of compression. And again, the smallest compression is typically the slowest. No compression is faster. And there is a certain level of encryption if that is an option that you want to go with. You start the process, you have a elapsed timer, and then eventually a estimated time left, and that is all over the place. And again, don't stress this one too much. We will have a lab outlining these steps, walking us through them one by one as well. After we've done our acquisition, we need to validate the evidence, because again, validating the evidence is probably the most critical aspect of our forensics investigation. It requires hashing the original evidence and our clone. The hash of both must equal one another. If they are not equal, then the evidence are not the same. And then you have to acquire the data or rehash it, or both. In Linux, again validating a DD acquisition, you can use an MD5 sum or SHA-1 sum utility that will do it. Some of the tools like DCFLDD will acquire the data and has hashing options as well. Windows has no built-in hashing algorithm for digital forensics. That is actually false. You can hash files using our PowerShell. PowerShell has hashing utilities built in. You can also use third-party if you want, but there are easily some PowerShell commands to hash with multiple algorithms, a source and destination, partition, object, file, folder, root drive, and more. Most commercial forensics tools also have built-in validation. The big thing is a drawback for RAW or DD is you may lose the metadata. Because raw format images don't contain metadata. There's normally a separate manual validation process for the raw acquisitions above just the hashing values. We can do RAID acquisition if necessary, and for that it can be very challenging, but we can use paid versions of FTK Imager or other forensics tools that are out there. Kane has a tool, and Paladin is also a very common open source forensics tool that can access a RAID array for acquisition. But you do have to keep in mind the design, the configuration, the size, the time it takes. The size is going to be the big one because we're talking about massive amounts of data. So again, RAID, redundant array of independent disks, normally 2 or 3 or more disks developed to work together. RAID 0 is basically we have 2 drives, or a minimum of 2 drives, half the data on one, half the data on the other. That way it increases the speed. RAID 1, we have a full copy of the data on both. A file written to one is written to both. The issue is you have to have 2 drives that are the same size that will work together. If one drive dies, for example, you have a complete backup or a complete copy of the data. With RAID 0, if one drive dies, you lose everything. Doesn't have redundancy, but speed is definitely increased there. So here again, with striping with RAID 0, you have data written to 2 or more drives. With RAID 1 mirroring, you have the same data written to both drives. If one drive fails, then you have a complete duplicate copy on the other storage device. There are things like RAID 2, 3, and 4. Those are not really common, but they are still out there. RAID 2 is similar to RAID 1. RAID 3 basically adds data striping and dedicated priority. RAID 4 is similar to 4, but RAID is written into blocks. Again, these are not common. These are not heavily used at all. RAID 0, 1, 5, 6, or variations of RAID 0, 1, 5, and 6, like RAID 60, or RAID 50, or RAID 10, or RAID 0 and 1, or 1.5, which these kind of are all the same. Variations of RAID 1 and 0 kind of put together. RAID 6 and 0, RAID 5 and 0. So there are some techniques that we can put together so that we can have speed of RAID 0 and redundancy from RAID 1. Here we have RAID 2 striping at the bit level. So we have files that are written to multiple drives and a parity. Parity allows us to rebuild if one drive fails. RAID 5, 6 are the big ones. RAID 5 basically allows a parity, so we have to have a minimum of 3 disks. 1 divided by n is the number of disks, is set aside for parity. That means 2/3 of the disk could be storage. If one drive fails, the parity on the other 2 drives can rebuild a single failed drive. That's RAID 5. If 2 disks fell, you lose all your data. With RAID 6, there's additional parity on each disk, so RAID 6 allows you to have the capability of having more drives fail. And again, RAID 10 or RAID 1 plus 0, there's RAID 15, 1 plus 5, there's RAID 16, 1 plus 6, and so forth. Here we have RAID 5. Again, we have it spread out over 3 or more drives, and then there's parity on each of the drives. That way, if one drive fails, we can rebuild the data. How do we acquire data from a RAID array? Well, we have to figure out how much storage we need. What's the type of RAID? Are all of the drives healthy and connected? Do you have the correct acquisition tool? That's a big one. I've done this where I started with one tool, spent days, realized it was not the appropriate tool, had to restart the acquisition. Paladin and a paid version of FTK Imager have really good acquisition tools for RAID, but again, you have to have the knowledge and the experience on how to use them. Another thing is, can the tool read a forensics copy of a RAID image? That's another big one. If the RAID image is too big, can you split the data? Copying small RAID systems to a large disk is possible. For example, right now I have a SAN with 500 gig SSDs. I can easily copy that to a 10 terabyte mechanical drive. The problem is we're going to lose some speed, but we can easily capture all 2.5 raw data of the SSDs and copy them to a 10 terabyte mechanical drive. So yes, you have to be, you can do smaller RAID arrays to a single disk when you have a large disk. So what are some of the tools? FTK Imager is one of the big ones. In-case, again, you can do it, but in-case is expensive and going away. X-Way Forensics is there, as well as other tools. A big thing to keep in mind, sometimes RAID systems are too large for static acquisition. Retrieve only the data relevant to the investigation or the scope that you have, instead of trying to get all of the sparse data. And again, there's pros and cons for that as well. In corporate environment, they may only want specific access to specific things, but if we're talking a criminal case and you're working with law enforcement and your scope says capture everything, then you're capturing everything. But at that point, you'll probably have the storage capacity to do a large array. So we've talked about all on-site acquisition. What happens if you want to remotely acquire the data? You want to sit down at a system and copy the image to a remote location. Can you do that? Sure. You can connect to a suspect's computer and over the network copy data from it. Again, you want to be careful. You want to make sure you're following all the appropriate policies and procedures of the organization. That way you're not modifying data from the suspect's computer. Remote acquisition tools vary in the configuration and capacities. Basically, you get what you pay for. Some open source tools are amazing, but their configurability is more complex than other tools. Drawbacks: accidental modification or accidental molestation of the data or the original evidence. You do that, the evidence might be thrown out of court. So we do have to be careful doing remote connections. AV, anti-spam, firewall tools all have to be able to be configured to ignore the remote access. And that means modification of the evidence. And with that, again, some court cases or some courts may not allow it. And the suspect could also have their own other additional tools for triggering alarms and may prevent the remote access. So we have things like ProDiscover. That's a incident response function. So this is a tool that allows us to capture volatile system state information, i.e. could be RAM, analyze processes currently running, locate unseen files and processes. Again, that's what the purpose of this tool, that's what it does. It can do hashing, look at the network connections, both IPs, port numbers, socket sets, where things are going, and again, it has the ability to do hashes. And it can create a hash inventory of all files remotely. So if you're looking at specific files, you can hash each file independently and have it done remotely so that you can modify or manipulate those files if you're analyzing them, and then you can see what's going on with them. I said modify specifically because if you open them and things like that, that might be modification, but you can always return them back to their original state, assuming you have a acquired copy of them. And you'd be doing all of that comparing the hash values. That way you can say, and you can forensically prove that the file you opened was the original file, and any modification that you may have done, opening, looking, navigating, all of that might modify it. The hashes, if they're identical, means the file is identical. With ProDiscover, we have things like PD server, remote agent, and a server installation. That way you can have a server running different agents on machines, and the agents will capture and send data back. Some agents are installed on the machine, some agents are booted off a live disk. Some of the tools with ProDiscovery could be password protection, working with encryption, securing our communication protocols, write-protected trusted binaries, and hashing and verification through digital signatures. We also have InCase that does the exact same thing. They have the ability to search and collect internal and external resources over a large area, supporting multiple operating systems, file systems, using their proprietary tool. InCase is super expensive, so that's not always an appropriate tool, but it is definitely there. We have other tools like our tools in our studio. They can create a raw format acquisition, and they support their own process. We have the US Lap Pro, which is a suite of tools developed by Whetstone. They can connect over the network and perform a live acquisition as well. We have F-Response as well, vendor neutral, that allows for the remote access and capability. There are different versions of F-Response: Enterprise, Consultant, Covert, Consultant Edition, and a Tactical Edition. And again, we're not going into the level of editions and what their tools are and how they're different. These are just so that you know that there are different tools out there, not just one. There are a plethora of tools for acquiring data both on-site and remotely, both statically and live. We have PassMark software, ImageUSB. That's basically a bootable flash drive if you have a new enough operating system, and that's downloaded from OS Forensics website, and that also has the ability to do a software write blocker. We have the ASR Data SMART. That's a Linux distro, and again, reading bad sectors, mounting write protected drives, accessing a drive without being mounted. But with ASR Data, you also have the ability to read and write data if that is on your scope. Runtime Data, I've used this actually a lot as well. This is for a shareware-based program for data acquisition and data recovery. I use Runtime for recovery, and that's specifically for Windows-based machines, FAT and NTFS, and it does work off of raw formats. We have the 9Imager, and again, bootable disk, designed only to work with its tool, and it can acquire single drive or RAID and more. We have tools off of SourceForge, like the Windows version of DCFLDD, or other tools that are out there. So again, the big thing for this chapter is understanding there's an acquisition process. You have to be able to store the acquired image in an appropriate format that you're able to work with, RAW being the most common, DD file extension probably the most common RAW version. We have different acquisition methods: disk to image, disk to disk, logical or sparse. Disk to image is probably one of the most common. There's again a plethora of tools out there. Most of the time, FTK Imager for acquisition, Paladin, which is I totally misspelled it, Paladin, and that is a open source forensics toolkit. In Windows, we have Autopsy and so much more. Again, when we're working with evidence, we want to make sure that we're not modifying the original evidence, so using a write blocker is a must. Lastly, we have acquisition tools like DCFLDD. That is an acquisition tool, not a file format like DD. DD is a file format. There are RAID tools out there if we're capturing RAID. There are remote tools if we're capturing remote options. And that is the end of this chapter. The big thing is, for data acquisition, we cannot molest the evidence files. meaning the original data cannot be modified. If you do modify it, it has to be heavily documented, and it may or may not be admissible in court. You want to hash the source, and when you do your clone, compare the hashes from the original and the clone. They should match. If they match, you're good to work off the clone. And again, always have more than one clone just in case. If you have any questions or concerns, definitely feel free to reach out. Thank you. All right, now that we've wrapped up some of the material for this chapter, are there any questions? There's a lot of different material covered, so again, the key thing is, as you're going through the material, whether it be the reading, whether it be the videos, ask questions, write questions down. The more that you can engage your brain in this material, the better you are at retaining the information. So again, questions, please feel free to reach out and we will go from there. Thank you, and I look forward to working with you throughout the remainder of these modules.